we're gonna use units. We're going to use scientific notation and order of magnitude to put numbers in perspective, essentially. And yeah, but before we do any of that, let's just do a little review from yesterday or Tuesday. I think I have a couple problems. Yeah, we got two problems. So we'll just kind of blow through these. These aren't anything really different than what we did the other day, but you know, why not? So suppose you're buying a car. Oh, and let me do autofocus before I forget again. Autofocus always turns off for some reason. So suppose you're buying a car for just under 16,000 and you manage to haggle for a 5% discount. Right? There is an 8.25% sales tax. How much do you pay in total for the car? And so I think I ended class almost on this problem, and I had tried to do it a really quick way by adding and subtracting the percentages. And as I thought it might work, and obviously it doesn't, because as I said, you want to make sure that these percents correspond to the correct number. So for instance, the sales tax will correspond to your final sale price. The discount corresponds to the initial sale price. So before I can apply the tax on the final sale price, I have to find out what 5% off of 15,99999 is. Right? So those are you have to kind of do it in two steps out of necessity, because if you try to do it all at once, you're going to take a sales tax on the initial sale price and not the final one that's discounted. So you'll be kind of spending more money than you should be. All right, so let's start with the discount. So 5% discount, and remember the formulas. So these formulas will come in handy, just in kind of daily life. So you have a discount. So what we did last time was we said that the discount price equals, so it's this initial price, 15 whatever, 99999. You gotta make yourself feel like you're spending less than 16,000, even though it's the same. And then you're gonna do, so you can do it as percents or you can do it as decimals. It obviously doesn't matter, but I'll do it as percents, maybe makes it easier. So 100%. So that's the total, that's the original price, right? If I just left it as 100%, it would just be 15,99999. But I want to take off 5%. So I subtract 5%. Right. And this isn't like that complicated of a formula, right? You probably could just have determined this on your own. If you're taking off 5%, you have 95% left. That's all it's saying. So, you know, but it's kind of nice that it's kind of written down. So I have this ugly number, 15,999. And then, as I said, that's 95%. Alternatively, you can write that as a decimal, which is what we'll need for our calculator. So it's just times 0.95. All right, cool. So let's see what we get. So let me clear everything. So 15,99999 times 0.95. And we get, so it's almost like $1,000 off. It's like 800, give or take. Once we round, it's like 800. So what is it? 15,199.99. So 15,199.99. So that's my discounted price. And as I said, now my sales tax will be 8.25% of my my discounted price. So you always have to always keep it in mind. Whenever you're doing with percentages, they always have a reference. They're always referencing some value. 8.25% of what, right? So it's always the final price, the final sales price. And then the 5% is referencing the initial value, what it was before you took off the 5%. Anyway, and so to apply a tax, you just do the opposite of what we did here. We'll do 100 plus the tax. So after tax price. So that's my final price. So that will be my final sale price, right? So that's the what we agreed upon to sell the car for. So that's 15,199.99, and then it will be 100. And instead of subtracting, since I'm adding a tax, I put plus, and then 8.25%. And so just like here, you can add the percents if you like. And when you do that, you get what, 108.25%. But just like in the previous part, to plug it in your calculator, you need to convert it to a decimal. And this one might not be as obvious, right? Because at 108.25%, you might be a little confused how to convert it to a decimal, just because it's more than, you know, like 95%. Clearly it's 0.95, I guess. But for 100, if it's not clear, you just divide by 100, right? So you 108.25 divided by 100. So you can always do that if it's not totally clear how to convert it to a decimal. So just to jog our memories, from percent to decimal, you divide by 100. From decimal to percent, you multiply by 100. So anyway, 1.0825. And I wouldn't really round this. 1.0825. You might be tempted to round it, but if you round it, you're essentially rounding the tax rate, which is not something people do, especially the county in New York State. So 15,199.99 times 1.0825. And so I get that number, 16,453 and 99 cents. So that's my final after-tax value. So if I was buying this car, that's what I'd have to go to the bank to get like a bank check for if I was paying in cash, or like that's what I'd have to get financing for, I guess. I don't know how that works, but you know, that's what you'd have to get a check for should you have been buying it in cash. Right? All right, so that's what we did yesterday, not yesterday. Let's just do one more, see what's up. But again, so these are the kind of the two formulas. If you're subtracting, if you're getting a discount of some percent, you use this 100 minus the discount. If you're adding some percent, like a tax, or it can be anything. It can be like maybe you gain interest at 3%. You do 100 plus 3, you get 103%. All right, same kind of idea. So this one combines everything. I thought it was clever. I don't know if anyone else will. But it combines percentages and units. So it's kind of like everything we've done so far in this little unit. Right. So the setup is we have 3 bags of dog food. Also, I was writing these notes while I was watching, what's that show? Unsolved Mysteries. Volume 2 is out on Netflix. So far, not as good as Volume 1, unfortunately. I don't know. The one took place in Sweden. The other took place in Japan. And I thought the whole bonus, the whole good part about Unsolved Mysteries is, I don't know if you've seen it, but it's that they kind of take place in like the United States. Like they're very like relatable. Like it's like small town America almost that they take place in. It's like, oh, this person was abducted. How did that happen? And it's in Japan. There's like a tidal wave or a tsunami. I don't know. It's not as fun, or it's not as spooky, I guess. Besides the point. So we have 3 bags of dog food. Bag A contains 3,500 grams of food. Bag B contains 15% more than bag A. And then bag C contains 2 pounds. If all the bags cost the same price, which is the best value? All right. So basically what we should do is we have to convert all of these to the same units. And we just have to see which contains the most food. Since they all cost the same price, the one with the most food in the bag will be the best value. And this is assuming that they're all the same quality. Obviously, if you're buying dog food, you probably don't want to buy the cheapest dog food for your dog. I mean, I guess you could. I don't know. I guess I don't buy expensive dog food for my dog, but I don't buy the cheapest. It doesn't matter. So, you know, there are more factors at play here in reality, but for us, we're just assuming it's the same quality. So the more, the better. Right. So let's see what we got. We have 3,500 grams. We have, this one has 15% more. So I think the best idea will be to convert everything to kilograms or pounds. And so maybe I'll do everything in pounds. We'll do that. Oh, you know, I don't know. Kilograms, do everything in kilograms, because this one is basically in kilograms, right? What is 3,500 grams in kilograms? Any ideas? Right, so there's 1,000 grams in a kilogram. So if I have 3,500 grams, I just have 3.5 kilograms. But if that's not clear, we can also do with the factor label method. So 3,500, and this is grams. And so if you did the homework, the homework 2, there's a bunch of questions, and it seems like there's a lot of questions on it. I should note, but most of them are very short, especially the earlier ones. Some of them are very short. You can pound them out in a few seconds or minutes. I guess seconds might be too short. So it seems like a lot of questions. You can get them done pretty quick, especially the first few. The latter half might take longer. Anyway, so as I said, 1,000 grams in 1 kilogram. Second. All right, good. And then, cool. And then the grams cancel, and I'm in kilograms. So as I said, I get 3,500 over 1,000 kilograms. And when you divide and multiply by powers of 10, you know it just kind of shifts the decimal place because everything we do is in base 10. But if you weren't sure, you could also just use your handy dandy calculator and get 3.5. So it's 3.5 kilogram. All right, so that's A. I'll put like an A next to it. Now bag B contains 15% more than bag A. So for bag B, I'll just take this 3.5 kilograms and add 15% to it, right? And we'll do it just like I did in the previous problem. So I do 3.5 times, and so I do 100%. That's my whole 3.5. And then I'm adding on 15. So plus 15%. Right.
If it's already 15% more, wouldn't that already eliminate bag A?
Yes. Yes, but you don't know how much bag B is yet. So C could still be the winner.
So it's essentially a contest between B and C, but you have to do A to find B.
Yeah, exactly. That's a good observation, though. Thank you for trying to make it shorter. But yeah, so we do what we've done. So 3.5 and then times, what is it? So it's 115%. Let me get that frame. So you do 115 divided by 100 to get it in a decimal form, but it's just 1.15. So 1.15. And I can multiply those together times, what is it, 3.5? So it's 4.025. 4.025 kilograms. Right, so just over 4 kilograms. It's 4 and like, I don't know what that is, a 50th, 20th, something like that. Not something, I don't know. 25th? Might be a 25th. Let me see. It doesn't matter. I won't double check. No, I don't know what that is. Anyway, so it's just over 4 kilograms. And now we need to convert the pounds. So this is B. Now we need to convert the pounds into kilograms. So I have 2 pounds for C. So 2 pounds. And we'll use the factor label method. How many pounds in a kilogram? Or how many kilograms in a pound, I should say? I think it's 2.2, right? So I have 2.2 kilograms in 1 pound. That's good. Yeah. I'm pretty sure that's what it is. Because
it's 2.2, I looked it up.
Oh, good. All right. And so they cancel. I know I never memorized these units. I was teaching, what were they? Nursing students. Apparently they have to know units. And I'm like, oh, I'm sorry. I don't know units. I mean, off the top of my head, I can use them, but I don't know what they are. Like the metric to imperial. Anyway, it's also odd. Nursing people round their units. So like a cup in nursing is 250 milliliters, but in reality it's 236. It's very odd. I don't understand how they do anything, but I'm still learning. Anyway, so you multiply them together, your units are in kilograms. So I get 2 times 2.2 kilograms. And that looks like it's gonna be bigger than B, but we can double check. I guess I'll put it here. 2 there we go, times 2.2, 4.4. I guess we could have done that in our heads. So in the end, we have 4.4 kilograms, and C is the winner. So if I was buying this dog food, I would buy C because I get a little more than B. It doesn't really matter. I mean, it is like half a kilogram, but that's only a quarter of a pound, loosely speaking. So it's pretty close all the way around. But that is your best bet. You get just about 1 kilogram more than bag A, which is like half a pound. So is that right? I don't know. I'm not good with metric. It's kind of like Celsius and Fahrenheit. I don't really know what Celsius degrees are. 50 degrees is warm, obviously, but is 37? I think it is. Any questions on these 2 problems? So this is kind of what we did Tuesday. All right. So today, as I said, we're going to kind of study how to feel around with units. And that kind of plays into the previous problem, right? Like I was saying, I don't really know what Celsius is. I mean, I kind of do, but I really don't have a really quick intuition about it. I would have to convert it to get a better feel for it. But so one of the things we're going to talk about outside of scientific notation is putting things in one unit in another unit to make them more understandable, right? So we'll get there. I think it's just after this. But yeah, again, just trying to get a better feel for numbers and units and using them and things like that. All right, so we can write any real number in this form where E is between 0 and 9. So E is like, I don't know, like 4.78 or 9.997 or 0.00001. And then B is an integer. And it can be negative. So it can be negative or positive, right? It can be like -2. It can be 16. It can be 400 million. It can be anything as just a negative or positive integer. Right? And so when we do this, we say n is in scientific notation. Scientific notation. So side note, on your a lot of calculators, like, so on the TI one, I don't think it does it as much or as frequently, but on these small calculators a lot, if you do really big computations, like, I don't know, let's try this, 100 times a bigger 100. Yeah, you get this. Like, so on this one, it's kind of nice actually, but it's saying it's 1 times 10 to the 13. A lot of calculators, especially older ones, will just tell you like 1 and then E13. And what it's telling you the same thing. It's just, it's telling you it in kind of a shorthand because it's a calculator with a little LCD screen, so it can't display nice pictures like this one can. But so yeah, so if you ever seen an E and then a number on a calculator, it's probably putting that number in scientific notation for you because it can't display it normally. And that's really where scientific notation comes into play. It comes into play when you have really, really, really big numbers. Like I multiplied, I don't know, 10 to the 7 times 10 to the 6 or something. Or really, really, really small numbers. And I have some examples of those in the next few pages. But if you do things in like chemistry where you're talking about atoms, or if you take like a physics course that talks about like the age of the universe or planets or anything in astronomy, you often will see scientific notation just because things in that realm are so big and tiny. All right, but let's just try some examples before we get too deep into applications. So these are just some random numbers that I popped up. And there's kind of a quick way to do it. So we're going to look at the decimal points. And so this is an integer, right? It's 3,065,123. I'm surprised I was able to say that. Sometimes I can't say numbers. But anyway, since it's an integer, the decimal point is right at the end, right? And so one way you can convert really easily to scientific notation is you want to just move the decimal place such that I figure out what this E is, because remember this E is between 0 and 9. It can't be less than 0. I guess it can be negative, I suppose. I'll put a plus or minus in front of it. Basically, if you want it to be between 0 and 9, it could be negative, but in that range, if you know what I mean. So, for instance, for this first one here, I'm going to move the decimal place 1, 2, 3. And then 4, 5, 6. So move it 6 places to the left. All right. And so
now, why are we moving it specifically 6?
Because I want it to be right after the 3. All right. And you'll see. So so I can write this basically is I can do it 3. And then I left the decimal place right after the 3, right? So it's going to be 3.065123. And then I said I moved it 6 places. So that's times 10 to the 6. So this number is exactly this. If I were to multiply this out in my calculator, I should get 3 million. We can check. Oops. Let's see. Again, this might put it in scientific notation, which doesn't help us, but we'll see. 3.065123 times 10 to the 6. Hey, 1230653. All right. So basically, when you move the decimal place to the left, you're factoring out a 10, right? So I don't have any smaller examples here, but if I did like 10.1, right? And I move the decimal place 1 to the left, then I can write this as 10. Well, I'll put 1.01 times 10, right? So if I move the decimal place to the left, you can think of it as just factoring out a power of 10.
So it doesn't matter how many times you move it, you just have to, like, your number of swooshes, you just do that by the 10th?
Yeah. So the number of swooshes will be the power of the 10. And then the number in front will be basically, it will depend on the situation, but like here, for instance, the number in front is just the first number dot the remaining numbers until you get to the end. But we'll do some more, and that won't always kind of work because we have like number 3 here has a bunch of zeros in front of it. So we'll have to see what happens in that case. But when it's an integer, it will always be like that. Yeah. And yeah, so this is just, you're just putting it in this format. And that's just what we define to be the scientific notation down here. So E is between 0 and 9. And I said it can be plus or minus. But again, it's just a format. It's just like you're deciding to put it in this form. There's nothing special about it. Conceivably, you could have put the decimal place after the 0, and you could have done something similar there. All right, so it's just a format. Let's try this one. This one is a decimal right in front. So for this one, what we want to do is, as I said, we want to get it to be, we want to have an E. We want to have this E number between 0 and 9, and maybe plus or minus. So to kind of make that come out, if you have something like this, you can move it to the right now. So, and when I move it to the right, I'm multiplying by a negative power of 10 in my format. So here, for instance, it's 0.934. So if I move the decimal place to the right one, so one place to the left, oh, sorry, to the right, then I can write it as, so it'll be 9.34, and I moved to the right once, so I'll do times 10 to the minus 1. And now it's in the right form, right? So this is my E. My B is -1. And that writing it in this way puts it in scientific notation. Right? Again, if you use these really big numbers in your phone or your calculator, I should say, you'll write it in that way for you, kind of as a result, just because your calculator doesn't like to display things with a lot of zeros. Right? Let's try this one too. So this one has a ton of zeros, so maybe we'll get the point across better. So here, again, I want to move my decimal place to the right or the left until I end up with a number between 0 and 9. So here, if I move it to the left, nothing happens. I just get more zeros, right? So I need to move it to the right to get it right after that 3. So let's see, we have 1, 2, 3, 4, 5, 6, 7, I think. Trying to use my pen with not blocking it. Yeah, 1, 2, 3, 4, 5, 6, 7. Yep, 7, it looks like. So 7 places to the right. All right, and then it's right after the 3. And so doing it that way, I have 3, just regular 3. If you want, you can put 3.0, but you don't have to because it's just 3. And then times 10 to the minus 7. All right, and so again, the 3 here would be my E, and the -7 would be my B. And you always want to verify that your E is between 0 and 9, and I guess 0 and 10 really. And you want to verify that that's it actually. The B can be anything that's an integer. And so yeah, I guess I should revise this. I'm sorry. This should be 0 and 10, not 9. It has to be less than 10. So I should just wrote it in interval notation. Sometimes I forget what we've covered, but 0, E, 10. In interval notation, that's what you want. If it's 0, it's 0, so you can't write it in scientific notation. Well, I guess you could. It could just be 0. It doesn't make any sense. And then if it's 10, basically what happens is every time, if it's 10, you can then factor out another 10, and that would be represented in your B. So if you have an extra 10 in there, you would always want to factor it out. So you should never have a 10. So it should always be less than 10 and greater than 0. Okay. Do another one though. So yeah, but as you can kind of see, they're really not too bad. You're just counting really, and then writing it in the right form. And so here's another one. This one is bigger than 1, right? It's bigger than 10. So basically, we want to move the decimal place not to the right this time, but to the left, because I want to get it as just a number between 0 and 10. So I have 1 and 2. And that puts it right after the 4. So 2 places to the left. And now you're done. You just write it as, so it's 4.0912, and then times 10 to the 2, because there's 2 places. All right, and now again, this is my E, the 4.0912, and my B is 2, and all that fits within our definition. My E is between 0 and 10, my B is an integer, and we're fine. All right. So as I said, these are really used for numbers that are really big and really small. Any questions about getting them in this form though? All right. So another reason that they're useful is that they allow you to compute products and divisions really, really easily. And they also allow, I think we'll talk about this a little later too, but they allow you to compare things really easily. So, for instance, if I had some huge number and I had another huge number and it had like 26 digits and the other one had like 30 digits, it's kind of hard to compare the two numbers, like looking at these huge strings, right? But if I have them in scientific notation, you have some big number in front that's between 0 and 10, but then that power of 10, it's like times 10 to the 26 and then times 10 to the 30. You can immediately see how much bigger they are from each other, because it's times 10 to the 30 times 10 to the 26. So they're kind of similar. They're both huge numbers, obviously, but you can tell that they differ by a factor of like 4. Again, we'll get to that when we talk about order of magnitude, but that's kind of one of the reasons they're really useful too, is they not only do they allow you to do kind of easy computations with huge numbers, but they allow you to kind of understand the numbers better and to get a better handle on them just by looking, by observation, right? But anyway, so as far as computations go, they're really easy, because whenever you multiply two exponentials that have the same base, in this case, my base is 10, then I can just add the exponents, and it makes it really simple. So like for instance here, if I'm multiplying these two numbers both in scientific notation, the 1.2 and the 13.2, you just multiply normally. So I'll do 1.2 times 13.2. And this one isn't in scientific notation, I should know, right? Not in scientific notation, because it's 13.2. For it to be in scientific notation, it would have to be 1.32 and then times 10 to the 26. So that one isn't in scientific notation, but the idea will still work, right? We can still multiply these things. Anyway, and then 10 to the 3 times 10 to the 25. And just like I said, when you multiply powers of 10 together, you just add the exponents. So this ends up being, so let me do this first. So I'll do 1.2 times 13.2. So I get 15.84, which is whatever. And then times, it's 10 to the 28 now. So it's 3 plus 25. So that's 15.84 times 10 to the 28, right? So it's kind of neat, because, I mean, I would know that it was 10 to the 28 even without a calculator, because it's 10 to the 3 and 10 to the 5. Now, if I wanted to get my answer in scientific notation, all I would have to do is move this to the left one. And going back to my previous sheet, when I move it to the left, it corresponds to a positive power. So I would have 1.584 times 10 to the 29 now. Right. Cool. So, and as I said, there's nothing wrong with writing it like that. It's just that, strictly speaking, it's not in scientific notation. Now, you can still get a good gauge on how big that number is. It's massive. It's 10 to the 28. It's immense. It's an immense number. But, writing it in scientific notation is just, if you see it elsewhere, this is what they'll be doing. So just, keep it back your head. All right. And so, as I said, multiplying is really easy, and division is also really easy for the same reason, because when you divide two powers of 10, you subtract the exponents. So like here, it's a little hard to see, because for some reason when I put fractions in, it formats them very tiny. But it's 9 times 10 to the 15, and then 3.2 times 10 to the 4. And so these are both in scientific notation, right? Because 3.2 is less than 10, 9 is obviously less than 10. So they're both in scientific notation. Not that it really matters for this kind of computation, but, and so the way I handle this division is I divide the front numbers by each other. So I have 9 over 3.2, and then times, and now the tens I can kind of handle on their own, 10 to the 4. And just like I said, when you divide powers of 10, you subtract the exponent. So it'll be 15 minus 4. And it's also just not for powers of 10, it's any division involving the same base exponentials. Anyway, 9 divided by 3.2, 2.8125. 2.8125. And then as I said, it's 10 to the 15 minus 4 now. Okay, and so 2.8125 times 10 to the what, 11? Okay. So, and that's something we would have known too. So looking at this, I don't really know what 9 divided by 3.2 is, but I know that it'll be times 10 to the 11. And so if you're handling things like, if you're doing things like involving galaxies and distances and space, like it doesn't, this 2.8125, it doesn't really matter, right? I mean, it does, it's important still, but like this front number is sort of negligible compared to this 10 to the 11. Like if I'm comparing this number to another number, I'm really only comparing the 10 to the 11 to whatever the other exponential has in it, right? Because this number is the bulk of it. That's the base of this whole number is that 10 to 11. This kind of just gives you the digits of the number, but this tells you the massness of it. And so that's really, again, the use of scientific notation. It's just this quick kind of eyeballing and understanding of the numbers better. Here we don't really have any context. These are just numbers, so they don't make much sense. But if you do things in physics or chemistry, this is kind of what it's used for. And this is just an anti-example. Ignore that dot there. This is just an example to show you that you can't really do anything with addition or subtraction with these. So nothing really to do. Nothing can be done. Can be really done. All right. Basically, they multiply nice, they divide nice, but you can't, when you add them together, nothing really happens. If I write this out, if you want to kind of look at it, you get 10 cubed plus, and then remember when you have a negative in the exponent, all these negatives and exponents we've been doing, just push the 10 in the denominator. So I end up with 2 times 1 over 10 squared. And so like you can see that there's really not much I can do. I can't really factor anything out. You could try to get a common denominator, but what's the point? So as I was saying, there's really nothing you can do to simplify this to make it kind of look nice. So multiplying, dividing, you're good. You can look at the order really nice. You can look at what the power of 10 will be really quick, but when you add and subtract, nothing happens. All right, and this is where I've been talking about the entire time really. So the order of magnitude of a number n, basically of a number in scientific notation is equal to that b there. So the power of 10 that your number has in scientific notation is called the order of magnitude. And just like I was kind of talking about, it's used to compare numbers that are huge or really small. And like I have some examples on this page that kind of show that. So this one, first one here, let's find the order of magnitude. And so I should note, to find the order of magnitude of a number, you first have to put it in scientific notation. And then once you're there, you're done. That's it. You just take that B number, that power in the 10, and that's your order of magnitude. So here, the circumference of the Earth is 24,901 miles, which is amazing. It's huge. It's a huge number. Also, fun fact: was it the Greeks? I think they found this. The Greeks computed the circumference of the Earth. I think they had like a tower at one part of the planet, and then down, I think it was in Egypt, and then down further south in Egypt, I think it was in Egypt, they had another tower, and at a certain time of day, they were able to like compare the shadows and the angles or something. And if I'm remembering correctly, they computed the circumference of the Earth just pretty closely to that, which is absolutely phenomenal because it was ancient Greece. I don't know why they're in Egypt, but anyway, so people have known this number for a long time, but we're going to look at the order of magnitude. So what I'll do is just like before, my decimal point, I'll rewrite it 24901. And so my decimal point, it's an integer. So my decimal point is right at the end. If you don't have a decimal point, it's at the end, it's an integer. And so I want to make it 2.4901. So I'm going to move it to the left 4 places to left. And remember, when we go to the left, we're positive powers of 10. So I can rewrite this as 2.4901 times 10 to the 4. So the order of magnitude, and I'm just going to call it OOM. I guess OM would be probably better. Usually you don't put an of in an acronym, but it's probably okay. So order of magnitude, equals 4. It's that number there. All right. All right. So in the grand scheme of things, that 4 is not very big actually. There's like this next one here, the age of the universe in years. So it's, strictly speaking, apparently it's 13.77 billion years at its current estimate. I think the Earth is like 4 billion or something. And so let's see what that is in scientific notation, right? And so again, it's another integer. So my decimal, what's that? Wow, my dot is right at the end. So I'll maybe, I'll rewrite it down here. 13770, and then 6 zeros. 111111. My decimal is right there. Right. And so let's just count how many places. We need it to be right after the first digit to make it 1.3 whatever. So I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's huge. So this is, it's also a good example because so when I rewrite it, I can do 1.377, and all these zeros, you could put them in, but you don't need to. You can, yeah.
Just because I'm lazy and I know like each comma is 3, could I just count by the commas and then add 1?
You could do that.
Yes. Just because I'm lazy?
Yeah, that sounds good. You can do that. If there are no commas, you can put your own commas in. Same thing, but yeah. And so again, this is another example of why you would use scientific notation. So it's 1.377 times 10 to the 10 years. Right? So you kind of get around writing all these zeros. And if there could be 100 zeros there, and the only thing that would change my expression is I'd put another 0 on my 100 or my 10 there. So it would be, if there were 100 places, you put 10 to the 100th power. So, you can use it to write really big numbers with a lot of zeros really easily. That's the point, right? But yeah, 10 to the 10 years. It's like an unfathomable amount of time. It's absolutely crazy. And this last one here is size of an atom in meters. I don't know how accurate this is. I went on Wikipedia and looked for the size of the atom, and apparently it's like between 30 and 100 picometers or something like that, which is a millionth or something, a trillionth of a meter. I forget. So this is not for all atoms. I think it's certain atoms. Chemistry is not my thing, but this is what we're going with. If you do take chemistry and have a correction, just let me know. But until then, so here. If I can't go to the left, right, because this is a very tiny number. So here, instead of going to the left, like we did for this huge age of the universe, I'm going to go to the right because it's very, very tiny. And when I go to the right, I'm going to have a negative exponent, right? So let's see. I guess I'll write it down here again. So how many zeros do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 3. All right. So now we'll do the same thing. And again, you could just count the zeros like I did. So it's a little redundant, but I like the little swooshes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I want it to be just after the 3. So 11. So 11 places to the right. All right. And so it's going to be 3. And you could put 0.0, but you don't have to again, times 10 to the minus 11. And this is in meters. Right, so that one's just also, so this one's absolutely huge. This one's ridiculously tiny. Right, and you know, in chemistry and stuff, you probably wouldn't write this, right? Instead, you would write, I think it's picometers. I don't quote me on that though. They have a new unit. They have a different unit that corresponds to this power of 10. So it'd be like 3 picometers or 3 whatever it is meters. But you could also write it like this, of course. But it's just not practical, especially if you're doing these things all day long. Right? But yeah, so very tiny. And so you shouldn't really have any issues with writing things in scientific notation. And one reason is that, you know, if the number's big, you should have a big power of 10. If it's tiny, you should have a really big negative power of 10. So you shouldn't, if you ever forget which way to go, just kind of look at the number and be like, oh, this is very tiny, so it'll be negative. This is very big, so it'll be positive. All right. Any questions with order of magnitude, things like that? Again, use a lot if you take more science courses. All right. So now let's talk about, so we just talked about how we can write numbers in better and more insightful ways. Here we're going to talk about using units that provide us more insight into numbers. All right. So these two examples I think are pretty good to demonstrate it. But basically the idea is that, like this first one here, I have 2 times 10 to the 6 inches. And this is in scientific notation, right? So we're kind of using some of the stuff we just did. But this, we have no idea how long this is. Like it might be big. Like, what is it? 2 times 10 to the 6 is a million. So it's 2 million inches. So you might say, oh, that's a lot. That could be the circumference of the Earth. But you don't really know, right? It's definitely not the circumference of the Earth. And we don't have a good gauge on inches, essentially. So what we want to do is we want to convert it to a unit that kind of better uses, it's better suited to the size. And so a good one here is miles. So what I'm going to do is I'm going to convert the inches to feet and then feet to miles. Right? You could do kilometers if you're Canadian, but that would be first, you had to first convert it to centimeters. So what is it, 2.54 centimeters an inch? I don't think we have any Canadians here though. If we do, what can you do? So we have 2 times 10 to the 6, 10 to the 6 inches. And we haven't done any unit conversions. Oh, we haven't done any unit conversions with scientific notation yet. So you can always leave it in scientific notation and do your unit conversions at the same time. So I'll leave it here and see what happens. So inches, I want to convert to feet. So I'll put inches in the bottom, feet in the top, 12 inches in 1 foot. And then I want to convert it to miles. So I'll put feet in the bottom and miles in the top. 5,280 feet in 1 mile. And that's it. And that's put it in my calculator. Oh, and I want to cancel all these inches, feet, gone. All right, so it's just in miles like we wanted. Let's see what we get. There we are. So 2 times, and you know, in your calculator too, if you have a graphing one, you can enter it just in that format. So, and it will print it out. Sometimes it won't print it out. If it's too big, it will leave it in scientific notation. So just be warned. Anyway, divide it by the 12 and then divide by 5280. So 12, and then divided by 5280. So that's what it is. It's 31.6 miles. So 31.6 miles. All right, so that's kind of what I'm talking about, right? So you have 2 million inches, but it's only 32 miles. So it's kind of crazy. And that's the point. So like you want to take these units that don't make sense or in the context of the numbers attached to them and sort of convert them to a metric that we better understand. So again, in this case, we have a ton of inches, 2 million of them. And so that's only 32 miles, but it seems huge. Like if you were on a game show and you asked someone how many miles is 2 million inches, they probably wouldn't guess 32. They'd probably guess some number that's bigger, but it's just a factor of, you know, there's 12 inches in a foot and then 5,000 feet in a mile essentially. So it kind of adds up. Let's try this one though. This is kind of the opposite direction. Here we have 5.4 times 10 to the negative 3 tons. And so, you know, whenever tons are used, people always think it's huge, like, you know, an elephant or something like 2 tons, it's huge. But here, it's 10 to the negative 3. And kind of like the first one, it's hard to get an understanding of what that is, right? So we're going to do the same sort of thing, but instead of converting it to a bigger unit, we're going to kind of convert it down to a smaller unit. So we can do pounds, we can do ounces. Maybe we'll start with pounds and see what happens. I think pounds will work for us, but if not, we can go into ounces. Or, grams if you're Canadian. So we have 5.4 times 10 to the minus 3 tons. And when I say pounds, so that's 2,000 pounds in a ton. So I want to get rid of tons, so I'll put tons in the bottom, pounds in the top, 2,000 pounds in a ton. And so I can cancel the tons. And so my units work out, it should be in pounds. Let's see what happens when we multiply it together. And if you could use a calculator like we did, but the other thing you could also do if you were really bored is you could put this 2,000 pounds in scientific notation, and that would also give you an answer. We could do that, I suppose. Maybe we'll do that. We'll see. Let's do that. But again, you could also just use your calculator. But this is kind of fun. So 2,000. My decimal point's here, so 1, 2, 3. So it's 2 times 10 to the 3. Right? And isn't that kind of cool? Right? So I get 5.4 times 10 to the minus 3 times times 2 times 10 to the 3 pounds. Sorry for the scribbliness. This pen, I think, is dying, so I don't know. But yeah, so now I have 10 to the negative 3 pounds. I have 10 to the 3 pounds, and I'm multiplying them together. And so just like we said, when you multiply exponentials with the same base, you add the exponents. So minus 3 plus positive 3 is 0. And so altogether, I just get 5.4 times 2 pounds. Isn't that neat? And so just like without a calculator, that's about 10 pounds. But you can also check. So you do 5.4 times 2. So 10.8 pounds. There, sorry, I can't see that there. So it's just 10.8. Oh, and I've been writing pounds out for some reason, but pounds. So it's kind of fun, right? Like it's this odd scientific notation ton unit measurement, but in reality, it's just 10 pounds. And 2 million inches, in reality, just 32 miles. So
why is the abbreviation for pounds LBS?
I have no idea.
Like miles is the first 2 letters, but there's
I asked someone this the other day actually, and he didn't know either, and he was a chef. So what does it say? Oh, it's descended from the Roman libra, hence the abbreviation LB. I would never have guessed it. I don't know why it descends from Libra. It must be Roman in origin, I'm assuming. The unit is descended from, it is. It's descended from the Roman unit Libra. The English word pound is cognate with the German Pfund and the Dutch Pond and the Swedish Pund. Very interesting. It all comes from the Latin word libra poundo, which means the weight measured in libra. That's so cool. Poundo in Latin just means weight. So there we go. Isn't that fun? That's so if you missed it. So pound, it's all from the word libra poundo. So the abbreviation takes itself, it's abbreviation from the libra part, but our word pound comes from the second part, which has nothing to do with the unit of measurement. It just means weight in Latin. Now we know. I'm very excited. I'm going to tell this chef who didn't know what it was. Any other good questions? Love Wikipedia. All right. We'll end with this one. All right, because I don't want to go too far into 5 o'clock. Because I know people want to start to eat and such. I mean, again, I guess I don't. I'm not really eating at 5, so we could go to 5:15. But people like to leave, I think. So a bike path has a scale model of a solar system on it. Every kilometer on the bike path corresponds to 2 times 10 to the 8 kilometers in space. So that's the important part. So every kilometer corresponds to 2 times 10 to the 8 kilometers in space. So it's like a scale. Like if you've ever been to a science museum and they have a planetary system set up, and it's like on the wall, it will say like to scale, and it will say 1 foot equals some million of miles. It's the same kind of idea, except it's not in a museum, sorry, It's in a bike path. So how far down the bike path is the Earth? If the Earth is 1.5 times 10 to the 8 kilometers from the sun. All right, so it's kind of fun. So what we're going to do is, this is the important part, right? Every kilometer is equal on the bike path is equal to this many kilometers in space. So essentially it's a unit conversion. And my conversion is from kilometers in the bike path to kilometers in space. So it's, I'll write it up here. 1 kilometer on bike path equals this many in space. So 2 times 10 to the 8 kilometers in space. All right, and so what we're going to do is it's the same as like 12 inches equals 1 foot. If I want to convert from kilometers in space, I'm just going to multiply and divide appropriately. So I'll start with my kilometers in space. So 1.5 times 10 to the 8 kilometers in space, and then times. And so I want to go into kilometers on the bike path. So I'll put that in the top, kilometers on bike. I'll just abbreviate bike because I'm out of space. And then this will be kilometers in space. And so the kilometers in space will cancel. So the kilometers in space are kind of like their own little unit. And then the numbers are up here. So 1 kilometer on the bike path corresponds to 2 times 10 to the 8 kilometers in space. So 2 times 10 to the 8 kilometers in space. And since everything's in scientific notation, it works out that the 10 to the 8s just immediately cancel as well. Because I have 1 in the top, 1 in the bottom. And so I have 1.5 over 2 kilometers on bike path. Right? And if you wanted a decimal version, you could obviously just plug it in your calculator. So 1.5 divided by 2 is, oh, it's 3/4. Should be more obvious. So it's just 3/4 kilometers on bike path. So again, you're converting from kilometers on the bike path to kilometers in space, but it's no different than converting inches to feet, except our units here aren't inches or feet, they're kilometers in different settings. Any questions with that one? All right, so this next part just goes the opposite way. So in this part, it says, if Pluto is 23.5 miles down the bike path, how far is Pluto from the sun? So the first thing we need to do is, you'll note that this is in miles, not kilometers. So we first have to convert miles to kilometers. And I don't have my unit sheet with me. So let me see, kilometers in a mile. So I'll start with my 23.5 miles. And I'll just convert it to kilometers. And so let's see. So to do that, you use that unit sheet, use a unit sheet, or just Google it. I think I gave you a unit sheet, I don't remember. Just Google it, look the unit, and let's see. So according to Google, 1 mile equals 1.6, 0934 kilometers. All right, let me get rid of that now. Cool. So that's converting it miles to kilometers. Right? So the miles cancel, and I'm in kilometers. And you should know this is miles on the bike path. So this is going to be kilometers on the bike path. So let me multiply it out, and we'll do it in 2 steps. So I have 23.5 times whatever that number is, 1.60934. And so it's about 37.82 kilometers on bike path. All right, so Pluto, again, it's on a bike path. It's like a scale model on a bike path. So like you're biking down the bike path, and maybe you started, I don't know, at Venus, and you kept going. And so from the center of the bike path, like where the bike path starts, the Pluto at the end is 23.5 miles or 37.82 kilometers, right? And so what I want to do now is convert that to actual kilometers in space. And so I'll use the same relationship that I used up here, but just in reverse. So I have 37.82. Again, we're just like converting, so kilometers on bike path, just like we're converting feet to inches. So I'll put the kilometers on the bike path in the bottom because I want those to go away. Bike path. And I want to convert it to kilometers in space. And so we said that 1 kilometer on the bike path corresponded to 2 times 10 to the 8 kilometers in space. So now my bike path kilometers cancel, and I'm just left with 37.82 times that 2 times 10 to the 8. All right, so let me rewrite that on a separate sheet of paper over here. let's see. Here we go. So I have 37.82 times 2 times 10 to the 8 kilometers in space. And so you could put that in your calculator. But another way you could do it would be to get it in scientific notation and multiply them that way. So this 37.82 is not in scientific notation. So I can multiply it times 2 first. So for that, we need a calculator. So times 2. And so we get 75.64, right? So 75.64 times 10 to the 8. Oops, sorry about that. Times 10 to the 8 kilometers in space. And the only thing that's the problematic now is this 75, right? It should be 7.5. So I'm going to move the decimal 1 to the left, which means I'm going to pull out a positive power of 10. So this would be 7.564 times 10 to the 9 kilometers in space. All right, so we're just kind of scaling things. And the reason this is kind of applicable to this unit is because, you know, these numbers are huge, right? If Pluto is this many miles or kilometers from, what is it, from, I'm assuming it's from the sun, because it's the center of the whole solar system. So if it's this many miles from the center of the solar system, it's kind of hard to visualize. But if you scale things down to a bike path, you know, then it's 37 miles, 38 kilometers, I guess, sorry, from the start of the bike path. So it's the same reason they scale them down in like a science museum, just so you can get a better feel for the distances involved. All right, any questions? Awesome. So I think there'll be there's a homework due tomorrow, obviously. We've covered everything on it though. So if you have any questions, let me know. But I think, I'm not sure, I probably won't put a homework on this one strictly, but I'll put a problem like this on the test. So it won't be on the homework, but there'll be a problem involving scaling things like that problem on the test, and also involving like scientific notation and stuff like that. But yeah. If you have any questions, we can call it a day. I'll post, I think we'll do a project on this unit, and then we'll have a test. I'm still working on what the project will be, but I'm not totally sure yet. All right. So have a nice weekend, and send me an email if you have questions or you want to Zoom or something. All right. Ciao.